Namaste, my friend, and welcome back to NEET Physics with Typical Monk. This is class 7, and today we study the force that holds the whole sky together, gravitation. Sit with one quiet wonder for a moment. The same pull that makes an apple fall from a branch also keeps the moon circling the earth and the earth circling the sun. One single law, written by Newton, governs both. When Rhea first read that, she could not believe a falling apple and an orbiting planet obeyed the same rule. The day she truly saw it, gravity stopped being magic and became mathematics. Today, one idea at a time, we learn how gravity weakens with distance, how it launches a satellite, and why an astronaut floats. Take a slow breath. Let us begin. So what will you carry home from today's class? First, Newton's universal law of gravitation and the constant we call big G, the rule that every mass attracts every other mass. Second, how the acceleration due to gravity, G, changes with height above the surface, with depth below it, and with latitude across the planet. Third, orbital velocity, escape velocity, and how satellites stay up, including the geostationary satellite. Fourth, Kepler's 3 laws of planetary motion and gravitational potential energy, which is always negative. And fifth, the NEET drills, assertion and reason, match the column, and a full worked numerical, so that everything you learn today, you can also score with. Ready? One idea at a time. Let us start with the law itself, the one Newton gave the world. Every mass attracts every other mass. The force grows when either mass grows. Double one mass, and you double the pull. This is why heavier bodies feel a stronger tug. But the force also falls off with distance, and it does so as 1 over r squared. Move twice as far apart, and the pull becomes 1/4 as strong. This inverse square behavior is the heartbeat of the whole chapter. Near a planet, this force per kilogram is what we call g, the acceleration due to gravity, 9.8 meters per second squared at Earth's surface. And the same law rules the heavens. It keeps every planet in its orbit around the sun and every satellite in its orbit around the Earth. Arjun once asked why the moon does not simply fall down. The answer is that it is always falling, but moving sideways fast enough to keep missing the Earth. Now look at this graph carefully, because it tells the whole story of how gravity changes with distance from the center of the Earth. Newton's law says the force between two masses is big G times m1 m2 over r squared. And it is always attractive. Masses only pull, never push. At the surface, the force per unit mass is G, which equals big G times the mass of the Earth over the radius squared. This is the value you feel every day. Now, follow the curve outward. Above the surface, G falls as 1 over r squared. Climb a mountain or ride a satellite, and you weigh a little less. And follow it inward, from the surface toward the center. Below the surface, G falls linearly, straight down to 0 at the very center, because only the mass inside your radius pulls on you. And at the center, that inner mass is nothing. Let us make this variation of G concrete, because NEET asks about it every year. Go up to a height, h decreases. For small heights, it is roughly g times the quantity 1 minus 2h over r. Notice the factor of 2. Going up loses g twice as fast as going down. Go down to a depth d, and g also decreases as g times 1 minus d over r. Here, there is no factor of 2, because only the sphere of mass beneath you keeps pulling. Keep going down to the very center, and g becomes 0. Mass now surrounds you equally in every direction, so all the poles cancel. And across the planet, g is least at the equator and greatest at the poles, partly because the Earth bulges at the equator and partly because the spin subtracts a little at the equator. Prior, remembered it simply, you weigh the most standing at the North Pole. Time to solve a full NEET numerical. Together, slowly, the monks weigh. We want the escape velocity from the Earth's surface, the least speed at which a body, thrown upward, never comes back. Take g as 9.8 meters per second squared, and the Earth's radius r as 6.4 times 10 to the 6 meters. Step 1. Write down what is given. Surface gravity g is 9.8 meters per second squared, and Earth's radius r is 6.4 times 10 to the 6 meters. Never skip writing the given data. Half of Rohan's early mistakes vanished the day he started this. Step 2. Recall the formula. The escape velocity is the square root of 2gr, the speed needed to break completely free of the planet's gravity. Step 3. Form the product inside the root. 2 times g times r is 2 times 9.8 times 6.4 times 10 to the 6, which is about 1.25 times 10 to the 8. Step 4. Take the square root. The square root of 1.25 times 10 to the 8 is about 1.12 times 10 to the 4 meters per second. Step 5. The answer? That is about 11.2 kilometers per second, the famous escape speed for the Earth. Notice it does not depend at all on the mass of the object escaping. Now look at this orbit because it ties the speeds and Kepler's laws into one picture. For a body circling a planet, the orbital velocity is the square root of big Gm over r, the exact speed at which gravity bends the path into a closed circle. The escape velocity is root 2 times the orbital velocity, larger by exactly the factor root 2. Circle the planet at orbital speed, multiply by root 2, and you fly away forever. Now Kepler's second law. Drawn here, a planet sweeps equal areas in equal times. See the two shaded wedges. Near the Sun, the planet moves fast over a short fat wedge. Far from the Sun, it crawls over a long thin wedge, and the two areas are equal. And Kepler's third law. The square of the orbital period is proportional to the cube of the semi-major axis. A planet farther out takes disproportionately longer to go around. Liar used this once to find a moon's period without ever measuring its speed. Now sit up straight. These 5 lines are what NEET actually asks year after year. 1. The escape velocity is the square root of 2gr, which comes to about 11.2 kilometers per second for the Earth, and it is independent of the escaping body's mass. 2. The escape velocity is root 2 times the orbital velocity. Never confuse the two. They differ by exactly that factor. 3. The value of g falls with both height and depth and is exactly 0 at the center of the Earth. 4. Kepler's third law says the period squared is proportional to the semi-major axis cubed, and the geostationary satellite has a period of 1 day, so it hangs over the same spot. 5. Gravitational potential energy is negative. It is minus big Gm over r, and it rises towards 0 as the bodies move apart. NEET loves testing that minus sign. Let us drill the NEET way. Remember the 4 options. Option A, both statements true and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. An astronaut in an orbiting satellite feels weightless. Reason. The astronaut and the satellite fall toward the Earth with the same acceleration. Think like Arjun, check each alone, then the link. Is the assertion true? Yes. They float. Is the reason true? Yes. And does the reason explain it? Perfectly. Because both fall together at the same rate, the astronaut presses on nothing and feels no weight. Both true. Reason explains. Option A. Second one. Assertion. The value of g is less at the equator than at the poles. Reason. The Earth bulges at the equator and spins about its axis. Both are true, and the reason is exactly the cause. The extra distance from the center and the spin together weaken g at the equator. Both true. Reason explains. Option A. Third one. Assertion. Inside a satellite, there is no gravitational force on the astronaut. Reason. Gravity provides centripetal force for the orbit. Check the reason first. True. Gravity is precisely what curves the orbit. But that is exactly why the assertion is false. If gravity acts to bend the orbit, it certainly acts on the astronaut too. Weightlessness is free fall, not the absence of gravity. The assertion is false. The reason is true. Option D. A quick match now. Say each answer aloud before I reveal it. Escape velocity. The square root of 2gr. The least speed to leave a planet forever. orbital velocity, the square root of big Gm over r, the speed to hold a circular orbit. Kepler's third law, the period squared over the semi-major axis cubed is a constant. And gravitational potential energy minus big Gm m over r. Remember the minus sign. A bound system always has negative energy. If all four came to you before the reveal, this chapter is becoming yours. Here's a favorite new NEET format. I will read some statements. You silently count how many are correct. Statement 1. Escape velocity is independent of the mass of the escaping body. Hold your verdict. Statement 2. The value of g increases as you go deeper below the surface. Think carefully before you answer. Statement 3. The gravitational potential energy of a bound system is negative. So, how many are correct? Two statements, the first and the third. Escape velocity truly does not depend on the escaping mass, and the potential energy of a bound system truly is negative. But the second one false. G decreases as you go deeper, reaching zero at the center. It does not increase. That single reversal is the trap NEET sets, and now you will not fall into it. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. Escape velocity and orbital velocity are the same speed. It feels natural. Both are about staying in space. No? Broham believed this for a whole term. But here is the truth. Escape velocity is root 2 times the orbital velocity, larger by that factor. Circle at orbital speed, multiply by root 2, and only then do you break free. Myth 2. An astronaut floats because there is no gravity up in orbit. So high above the Earth, surely gravity has run out? The truth. Gravity is strong there, nearly as strong as on the ground. Both, the astronaut and the satellite, are falling toward the Earth together in the same free fall, so the astronaut presses on nothing and feels no weight. Weightlessness is free fall, never the absence of gravity. Time to test yourself, rapid fire. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just the ideas you built today. Question 1. What is the escape velocity from the Earth's surface? About 11.2 kilometers per second. Question 2. What is the value of g at the center of the Earth? 0. The mass all around you cancels. Question 3. Escape velocity is how many times the orbital velocity? Root 2 times. Question 4. What is the period of a geostationary satellite? 24 hours, 1 full day, so it stays over the same point. And question 5. State Kepler's third law relation. The period squared is proportional to the semi-major axis cubed. If those came quickly, you have truly understood today's class. Let us gather the whole class in one slow breath. Newton's law, the force is big, G times m1 m2 over r squared, and it is always attractive. The surface value G equals big Gm over r squared, and it falls with both height and depth, reaching 0 at the center. The orbital velocity is the square root of big Gm over r, and the escape velocity is root 2 larger than that. Kepler's laws. A planet sweeps equal areas in equal times, and the period squared is proportional to the semi-major axis cubed. Gravitational potential energy is negative, and weightlessness in orbit is free fall, not zero gravity. And next class, we turn to matter itself. Mechanical properties of solids, stress, strain, and Young's modulus. Do not miss it. And so, my friend, we have learned the force that reaches across the whole universe. It may have looked like just one law and a handful of formulae, but understand this single inverse square rule pulls the apple, holds the moon, launches every satellite, and steers every planet around its star. Newton saw one law where others saw two worlds, and today you saw it too. Arya, Priya, and Rohan all sat exactly where you are now, staring at that falling apple, and they learned to compute the sky. Be patient with yourself. Tonight, revise the g versus distance graph once, slowly, and say the escape velocity formula aloud. One idea at a time, you will crack NEET, of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, Keep going. I will see you in the next class.